continuing the video that we started last time, and in that video we were trying to find the eigenvalues and eigenvectors of this matrix, and we recall that the definition is AV equals lambda V, which is what I've got written here. So we found that one eigenvalue was 3 and the corresponding eigenvector was 2. So let's see if we can find we found the other eigenvalue was 5, and so let's see if we can find the corresponding eigenvector. So in order to do that, we need to go back to our system of equations and solve that for v1 and v2. Okay, so let's go ahead and put in lambda equals 5 there. Oops. So let's see. We have 7 minus 5 v1 plus 2v2 equals 0. I'm done. What? Okay. You know why that is? Whoops. I just okay, so I had a little issue there, but okay. So the idea is that this is 2v1 plus 2v2 equals 0, and I'm telling you that this is all you need for your eigenvectors, because your eigenvector will solve that equation. Now, how do I know that? Is because if I go into the second equation, that would be minus 4v1 plus 1 minus 5v2 equals 0. I would have minus v1 minus v2 equals 0. Notice that those are multiples of the same equation. And those are multiples of the same equation by design. So therefore, if you're stuck for time, you really only need to look at the first equation. And so, in fact, I'm going to go ahead and rescale it. v1 plus v2 equals 0 is my equation. And now I just need, for my eigenvector, I need any v1 and v2 that satisfies this equation. And so you remember our shortcut. If I have a v1 plus b v2 equals 0, I can just take my eigenvector to be the reverse of these, so that would be BA, and then negate either one, doesn't matter which one. Okay, and so that's a fast way of getting an eigenvector. So in this case, our eigenvector is 1 minus 1. Okay, and now if you did have time, you could check to see that this is an eigenvector, meaning you could take 7, 2, minus 4, 1 times 1 minus 1, and see that that is equal to, there's a question mark right there, 5 times 1 minus 1. And you should see that those are the same. Very good. So now, what have we just been able to do here? We've been able to find the eigenvalues and eigenvectors to that array. So let's use the same array, but now I'm going to try to solve x1 prime equals 7x1 plus 2x2, and then x2 prime equals minus 4x1 plus x2. Okay, so notice that that is the same matrix equation. 7, 2, minus 4, 1 times x1, x2. Oop, I'm running out of room there. Okay, good. So what we said is that our ansatz, our original ansatz, was that x of t equals e to the lambda t times v. Well, now I've got 2 lambdas and 2 v's. And so just as in chapter 3, we're going to list a little bit of theory. Yeah, did I put an e in there? Theory. 1. So this is, are you going through the notes? This is page 3 of our notes here. If lambda 1 and v1 and lambda 2 and v2 are evals and evx for matrix A, then we get that e to the lambda 1 t v1 and e to the lambda 2 t times v2 each separately solve my equation, my original equation. 2. In fact, what I can do to get a general solution is I can take a combination of those two. So that's c1 times e to the lambda 1t v1 plus c2 e to the lambda 2 t v2. This is going to be my general solution. So is this sounding familiar, by the way? General solution. Is this sounding like chapter 3? Because in chapter 3 we had almost an identical situation, except that we didn't have the vectors v1 and v2. Okay? And so this is going to be a general solution if lambda 1 is not equal to lambda 2. And that's the situation that we're in right now. Okay? And so for our system of equations then, our general solution is going to be x of t equals c1 e to the 3t. Let's see, what was my eigenvector for the lambda equals 3? Do you remember? 1 and 2, wasn't it? 1 and negative 2. 1 and negative 2 plus c2 e to the t, 5t times 1, negative 1. Okay, there it is. That is our general solution to our differential equation. Very good. So let's see if we can do another one just from scratch here. So, whoops. What just happened there? Got things flying around here. Okay, I'm not sure what I pressed, but we'll continue. Okay, why isn't the... Okay. X of prime equals 3, 1, 1, 3, x. Let's just go ahead and solve this from some start here. Let's see if we can do it in 3 minutes. And so I get my trace is 6, determinant is 9 minus 1 is 8, and so that means lambda squared minus 6 lambda plus 8 is equal to 0. Does that factor? I hope so. Let's see, how about 2 and a 4, huh? Minus 2 minus 4. So lambda equals 2 and lambda equals 4. And now for lambda equals 2, we find an eigenvector. And so that's going to be 3 minus 2 times v1 plus v2 equals 0. And remember, this is my shortcut. I'm not going to bother with the second equation, although you could write it down. This is v1 plus v2 equals 0, or v equals 1 minus 1. Do you remember our shortcut for that? It's good to remember the shortcut. And so for lambda equals 4, we have 3 minus 4 times v1 plus v2 equals 0, which is minus v1 plus v2 equals 0. And so my vector there is going to be just 1, 1. Good. And so now we have our solution. The solution is x of t equals c1 e to the 2t times 1 minus 1. Notice that the lambda and the v go together, right? These are paired together. Plus c2 e to the 4t times 1, 1. There you go. That is the solution to the differential equation. Good. So now we know how to do that. What's next? That's really... Oh, let's try one out here, just for fun. Let's take this equation that we just solved, and let's convert that to second order differential equation, just to compare this to chapter 3 methods. So comparing to chapter 3, if I have x1 prime is equal to 3x1 plus x2, that's my first equation. x2 prime is equal to x2 plus 3x, x1 plus 3x2. Good. Then to make this into a second order differential equation, I solve for x2, right, in terms of x1. I plug that into the second equation. Oops, that's a single derivative, sorry about that. Equals x1 plus 3 times x1 prime minus 3x1. Good. And now let's go ahead and simplify that. X1 double prime minus 3x1 prime equals x1 plus 3x1 prime minus 9x1. Good. And now we get x1 double prime minus 6x1 plus 8 x1, oops, that's x1 prime, x1 equals 0. Does that look familiar? There's my characteristic equation. What did we get for the characteristic equation up here? Oh, is that a coincidence? No, it is not. So actually, our x1 of t, in this case, x1 of t could be written as c1 e to the 2t plus c2 e to the 4t. And then from this, how would I get x2? Well, x2 of t we wrote up here is x1 prime of t minus 3x1. And so you would plug this in to get your x2 of t. Now I should warn you that the c1 and c2 that we found down here are different than the c1 and c2 that we found here. Whoops. Oh, actually they are the same. So strike that. It's just coincidentally they are the same in this case, but in general they would be different. Okay, I've run out of time. We'll pick it up here in the next video.